Good evening, everyone. Good evening. How's everybody doing? Thank you for coming. How many particle physicists do we have in the audience? How many want to learn about particle physics? You're at the right place, hopefully. A few house rules before we start. Please mute your cell phones so that it doesn't ring while we're talking. And then the bathrooms are outside the hallway on either side. This lecture is being recorded and it will be uploaded to our YouTube channel about a week or so from now. So my name is Tokumba Ogunfumi. I work here at Santa Clara University as a professor of electrical and computer engineering. I also serve as co-associate dean for mission, culture, and inclusion in the School of Engineering. It's my pleasure to welcome you all to the third distinguished lecture on diversity, equity, and inclusion in the School of Engineering. Thank you for joining us in person because we have missed in-person meetings for a while. So thank you for coming. This lecture series is a new lecture series approved by the Dean of the School of Engineering, Dr. Elaine Scott, as part of a diversity, equity, and inclusion initiative. The goal of the program is to invite successful, distinguished, underrepresented minorities, scientists and engineers who can serve as role models and give a university-wide lecture. We want to expand the picture of success. It can be a challenge for students to envision their own career if they don't see people like them in those positions. So this series is supposed to shine a light on what's possible and inspire the next generation of STEM professionals. We put together quarterly presentations. So this is the one for this quarter, and it's the third in our series. We have guest lecturers from industry, from academia, from research, and they come to tell us what they have done in their professional life, as well as challenges to help us improve on our diversity, equity, and inclusion goals. Today, we are honored to have Dr. Dominguez to give us this third lecture series. I would formally introduce him later, but for now, we want to welcome him to our campus. And we are lucky to have the acting provost, Ed Ryan, to come and welcome our distinguished guest. Please come.
Well, hi, my name's Ed Ryan. On behalf of Kate Morse and myself, we're so happy that you're here. I had the opportunity to attend the lecture series in the fall, and I think it's such an important opportunity for so many reasons, and so happy that you're here today. And we had a chance actually to connect in the summer when he was on a college tour, and hopefully we will be successful in wooing his daughter here. So, sorry about that. No pressure, based on what I'm talking about.
Physics major.
But one of the things I wanted to say, and I said this a little bit in the fall, one of our former presidents used to say, the world needs Santa Clara. And I thought that was a fairly bold statement, but the more I think about it, I really think it's true that I think Santa Clara offers a unique and distinctive education. It's not just about training future physicists or future engineers, but it's teaching them, training them to be global citizens who care and use the training they learned to improve humanity, broadly speaking. And I think the work that the School of Engineering's done has been so important, not just in training future leaders, but also in recruiting a diverse set of students. And so I look at Ruth, I look at Ray in the back, and I know that the work you guys have done for so long has been so impressive to make sure that we have a diverse set of students, both in terms of gender, in terms of diversity. And so happy that this is another opportunity to really, I think, showcase to students what it means to be a leader and a leader in service. And so happy you're here today. Thank you for coming and look forward to the great talk. So thank you.
Thank you. We are also lucky to have in attendance the Dean of the School of Engineering, Dr. Elaine Scott, who would also come to welcome you all and welcome that distinguished lecturer.
Thank you very much, and I'd like to welcome Dr. Dominguez. Just so thrilled he could come here all the way from the East Coast. I'm so happy that we were able to offer him glorious California weather today, so that's worked out pretty well. But I want to thank you all too for coming, and this is really a chance to celebrate inclusive excellence within not only the School of Engineering, but overall STEM as well. So it's a great opportunity to begin our collaboration with the sciences, get engineers and sciences together, and more activities like this. So one of the things that this series brings about is really an opportunity to bring everyone to the table to really listen to what people from very diverse backgrounds have to offer and bring them together in order to celebrate their successes. So with that, I would like to turn it over to Dr.
It's a mouthful. Thank you so much. I appreciate it. Okay, now it's time to introduce our distinguished lecturer. This is the advertisement that we put on, but there's a lot more, so let me put this on now. I have a lot of pages to read, so bear with me. Aaron Dominguez is a provost and an ordinary professor of physics at the Catholic University of America. His main area of research is in particle colliders to search for new physics, including the recently discovered Higgs boson. His area of expertise is in instrumentation, designing, building, and using silicon-charged particle trackers as precision tools to reconstruct the complicated interactions taking place in these collisions. He received his undergraduate degrees from Whitman College and Caltech, his PhD in physics from UC San Diego, and was a postdoctoral researcher at Lawrence Berkeley National Labs. In 2005, he was a recipient of the NSF Career Award. He has played numerous leadership positions in the L3, CDF, and CMS particle physics experiments at the CERN Laboratory in Switzerland, and also at Fermilab in Chicago. Specifically, he just recently finished being the deputy project leader that's funding the US efforts of 9 universities to improve the silicon pixel detector, hadron calorimeter, and trigger in preparation for high luminosity runs of the LHC in coming years. He has mentored 7 postdoctoral researchers, 3 graduate students to completion, 3 currently in progress, and numerous undergraduates. He's a member of the National Science Board, serves on several advisory boards, including QuackNet, and is an author on more than 1,100 papers in experimental high-energy physics and instrumentation. I wonder if he has time to sleep. It's a lot of papers. Anyway, prior to becoming the provost of the Catholic University, Dr. Dominguez served as the dean of the School of Arts and Sciences. Previously, he was professor of physics and astronomy and associate dean of research and global engagement at the University of Nebraska, and a postdoctoral researcher at Lawrence Berkeley National Labs. As a provost, he is the chief academic officer of the university and serves the academic life of Catholic University's 12 schools, its libraries, research institutes, and the Catholic University of America Press. He aims to change the course of student lives and propel them toward a meaningful future. Provost Dominguez's mission, together with faculty, students, and staff from all faith backgrounds, is to raise the Catholic University of America to a strong voice in the conscience of higher education. He's actively recruiting faculty and other leaders who will carry the research and Catholic missions forward together, building academic and professional programs, cutting-edge laboratories and facilities, and establishing institutions to serve humankind through Catholic social doctrine. Now, please join me in welcoming Dr. Dominguez to the podium. Thank you.
Thank you. Thank you all very much. Let me switch here to. Thank you all very much for having me here today, and for the beautiful weather. It's true. So as the provost, I subscribe to the District of Columbia's alert system, in case there's an emergency. And the alert I got this afternoon is that there's a hypothermia alert in the District of Columbia. Meanwhile, you guys are wearing shorts outside over here. So thank you for that. I want to talk today is kind of two talks. I want to tell you a bit about how the international field of high energy physics works, what we've discovered over the past several years, and to weave that into a bigger question about the development of the STEM workforce in the United States, and what a place like Santa Clara University, your role in this important strategic need for the United States. So what is particle physics? It's the study of the fundamental constituents of matter, the rules for putting these fundamental building blocks of the universe together. In other words, what's the world made of, and how does it work at its most fundamental level? And we've had great success over the past really 100 years or so at understanding what the world is made of and what it and how it works. But it turns out we're only getting about 5% of it correct. Amazingly, 95% of the universe is made of unknown stuff, and we've only recently realized that we didn't even know something that we didn't know. So I'm sorry, but if I were in physics class, you take an exam and get 5%, that's an F. So we're sort of getting an F from God right now, but that's okay. And then I want to tell you a little bit about our most recent big discovery in particle physics called the Higgs boson, which is central to my own particular area of research. So the universe really was created out of nothing. It came into existence about 13.7 billion years ago from nothing. It wasn't empty space with a pile of stuff that blew up. There was no space, there was no time, there was no nothing in it. The inception of the universe came from that. Here we are, 13.7 billion years ago, because of the way that happened. Having this conversation this afternoon in this particular part of the cosmos, over here in that large cluster. There's our local cluster. There's the Milky Way. We're about right there in the spiral arm. There are nearby stars. There's the sun. On this planet, orbiting about 100 billion stars. They're near, on on a planet orbiting one star out of about 100 billion stars in our galaxy, in the middle of about 100 billion galaxies. So that's the brief history of time till this afternoon.
I feel really small now.
Here's a map of our world, and there's a little red pin on the institutions that collaborate with me and my colleagues on the compact muon solenoid experiment at the Large Hadron Collider in Switzerland. So each little pin represents a particular institution, mostly universities, but also some national laboratories. And so you can see that this is a worldwide effort that we have going on at Switzerland with this Large Hadron Collider to really understand this basic question of what particle physics is all about. So about 10,000 of these inhabitants on this planet came together to build what is, in fact, the largest scientific instrument ever built by mankind, to study these questions of the basic building blocks of the universe, and then to ask these other questions about what does it mean and what's our place in it. Here's an aerial view of the Large Hadron Collider in Switzerland. Here you can see, I've got the pointer here. Here you can see, you cannot actually see the accelerator ring, just what's drawn in yellow, from space or from the air because it's underground. So you could just see pastures and houses and whatnot, but it's under there. It's about 100 to 150 meters underground. The Geneva airport is right here. It's about the size of your San Jose airport. So you can see how big this collider complex is. There's also other subcolliders that help accelerate the particles up to speed as they get injected into the Large Hadron Collider. This little dotted line is the Franco-Swiss border. So this bit over here is France. This lake over here is Lake Geneva. So the Franco-Swiss border actually crosses through our accelerator and our laboratory and our office complex, which is right here. So the border literally runs right through like our office. Imagine you built Santa Clara University like right on the border with Mexico or something. That's what this is. And they did this deliberately, in fact. They did this deliberately at the end of World War II to build an international laboratory to study at the time nuclear physics in a peaceful manner. This is after the destruction that was wrought after World War II. Here's a photograph of the underground in this tunnel. So you can see it curving off into the distance. I don't know if it was mentioned on the slide before, but it's about 30 kilometers in circumference around. So you can see it curving off in the distance. This is I think it's about 10 feet tall down inside of the tunnel. And you can see this is part of the accelerator magnet and accelerating cavity complex. This is when it was being installed. It doesn't usually have wires hanging out like that. But you can see it's a confined space. It's well, everything's kind of packed in there. And this is 100 to 150 meters underground. This accelerates protons in opposite directions using superconducting magnets and superconducting radio frequency cavities. And we use liquid helium to cool the materials that make these superconducting magnets down to about 1.7 degrees above absolute zero, 1.7 Kelvin. And that's because that's the temperature you need to cool those particular types of materials so they become superconducting. So not only is this the largest machine ever built by mankind, it's the largest cryogenic mass in the world. And unless there are a race of aliens with a larger super collider, it could be like the coldest place in the universe, the largest, coldest place in the universe, because it's colder than outer space. The average temperature of outer space at this particular time is about 3.5 degrees Kelvin. So it's even colder than sort of your average cold, dark spot in outer space. There's a schematic of the accelerator complex that it takes to get things injected into the LHC, the big ring. It starts off with some linear accelerators that inject the proton beams into these other rings that get it going up into higher and higher energies, faster and faster, in other words, until it's injected into the Large Hadron Collider. Here's a photograph of our experiment in the experimental cavern, and this is our detector that we built. Currently it's in the open position so that we can access it. You can see how large this thing is and how complicated it is. The beams go right through the middle of the experiment, the detector right here, in opposite directions, and collide right at the very heart of the experiment. And this apparatus is a way to capture and image the radiation that comes from the nuclear explosions that are happening every 25 nanoseconds. So you can see it's a tremendous engineering feat, right? Every one of these detectors has power and cooling. Every one of these detectors has some kind of signal readout, and every one of those cables, wires, and cooling elements has to work. So what is the universe made of? The stuff that you can see with your eyes when you look on a dark night, stars and galaxies and things that shine, is only about, it's less than 1% of the matter energy content of the universe. These things called neutrinos, which are sister particles to electrons that are produced first in the Big Bang, and then secondarily through the shining of stars. The operation of stars create lots of neutrinos. Neutrinos have a mass, it turns out, and there's many, many neutrinos in the universe, and they constitute somewhere on the order of 1% of the matter energy content of the universe. And these are the things that we know about, like we know what these things are. And then the other stuff that you can't see that's out there, dark things, but which are made of stuff that we know, represent around a little less than 5% of the matter energy content of the universe. So that's the 5% I mentioned in the opening statement. That's the stuff that we know about. That's the stuff that we spent all of human civilization, getting to, is that 4% there. Then there's this stuff called dark matter. And it should really not be called dark matter because it's not dark like a dark cloud that obscures light or obscures things. It's really more like invisible matter. And we know that it's there because if you look at the rotation speeds of stars and galaxies, the galaxy's not working correctly unless there's other matter that's out there affecting the speeds of the stars. And this has been known for quite a long time. And we haven't been able to come to a fundamental understanding of what this dark matter is. We just know that it's there. It interacts gravitationally with other matter, like me and you, but it interacts so weakly in any other of the three forces of nature that it's practically invisible. So there's dark matter streaming through you right now. But you can't feel it, right? But it's there affecting the rotational speed of our sun around the rest of the Milky Way. So, and there's a lot of it. There's, 5 times more of it than the stuff that we know about. So that's a big clue. This is the unexpected part that's the most recent big under discovery, that there's this thing called dark energy. Again, it's not a great phrase. It basically encapsulates our complete ignorance of what it is, but what it's doing, it's acting in a sense like an extremely powerful anti-gravitational force that's causing the universe to continue to accelerate. When if it were just gravitation, things should be slowing down. It's in fact going faster and faster. There's something else that's pushing the fabric of the universe apart in an accelerating fashion. And then finally, the universe has essentially zero antimatter. So why does that matter? When in the Big Bang there was an equal amount of matter and antimatter created to conserve the types of conservation principles that you all learn in your introductory physics classes. So for every electron that was created in the Big Bang, there should have been an anti-electron, and etc. for all of the other fundamental particles. But we see no antimatter left. So in fact, the real question is, why is there any matter left? Because when an electron and anti-electron interact, they annihilate and create a photon. So why are there any electrons left? Somehow the universe has a small favoritism for the stuff that we're made of, and an anti-favoritism for the antimatter. And if it were perfectly conserved, if there were perfect symmetry between matter and antimatter, we wouldn't be here. There would be no us. So that very small asymmetry is obviously extremely important. Otherwise, there wouldn't be the kind of universe that we live in. And we can produce this antimatter in these colliders and study it directly, and that's in fact what we do. I think I'm going to turn off this lapel mic because it's giving some feedback.
It's my fault.
So here are some of the big questions, and then I'll get into a little more of the details. So, what are this part? The world of particle physics is quite large in terms of the types of questions that we pose and that we're able to answer. Are there other laws of nature? Are there new symmetries of nature? What is dark energy? Are there extra dimensions? It is possible. There are theories that propose the existence of extra dimensions, and it's not easy to observe such a thing. But there are possible scenarios where we could observe a particle going in and out of one of these extra dimensions in our experiment. Do all the forces unify into one sort of master force at the highest energies? Why are there so many different particles? Why is there not just 2 or 3 different types of fundamental particles, but instead many that do exist? What is dark matter? Is it a fundamental particle? Is it a series of fundamental particles? Is it some new type of force that leads to these types of particles? What is it? We just know that it's there. Neutrinos having a mass is also quite strange. We don't know the origin of the mass of neutrinos necessarily. I'll tell you how it is that things like electrons and quarks and stuff that we're made of get their mass from the Higgs boson. We're not sure exactly how neutrinos get their mass. How did the universe come to be? That's like the big theological question, which we can discuss at a Catholic university quite freely. But scientifically, there's no really great explanation for how the universe came out of absolutely nothing. Where's all the antimatter, and why is gravity so weak? So gravity, I'll just say one word about it. It's it's the first fundamental force that was discovered by Isaac Newton, in a sense. But it's extremely, for having known about it for so long, it's been the one that we've had the hardest time understanding at a very fundamental level, at a quantum mechanical level. And it's because it's extremely, extremely weak compared to the other 3 forces of nature, like the electromagnetic force and the strong forces, the nuclear forces. And so here's an example of how weak it is, right? This little clicker is made of stuff, made of plastic, and the electrons from the plastic in my finger are repelling each other through the electromagnetic force, which prevents me from putting my finger through it easily. And yet, I can defeat the entire pull of the planet Earth by moving it around. So the whole planet is weaker than my little arm here, right? So it's a huge difference in scale of forces, and we don't know why. And in fact, it could be that extra dimensions is one reason. It could be that gravity is shining into one of these extra dimensions, making it appear weaker to us in the 3 dimensions that we're, or 3 plus 1 dimensions that we're stuck in. So we can't expect to answer all these questions, but we actually do have a shot at answering many of them, and particle accelerators in these telescopes and underground detectors are really, really fantastic tools that we've developed over the past several decades. And this is how they work. So I'll give you an example of the basic principle of how these particle detectors work to see what happens when we collide these proton beams together. So you all know the electromagnetic spectrum, right? Photons at different energies or wavelengths. So here's one object in the sky, one physical object in the sky, this Crab Nebula, which is a remnant of a recent supernova, seen through different detectors, different telescopes. So the same object seen in different parts of the electromagnetic spectrum. So you can think of it as the same thing viewed with different forms of radiation, right? In this case, photons at different energies. And it's the same thing, and with these different types of radiations, you can see the same image, but in different details. You can see different parts of the same thing with different parts of this electromagnetic spectrum. In the long wavelength, the very large array, with radio waves, you can see the image up on the top right. With infrared radiation, so at higher energies, but still not in visible light, you can see the image there in the middle. With the Hubble telescope, with the kind of light that our eyes are sensitive to, you see that image. And every time you start seeing different parts of the same object, right? Until you get down to X-rays, and you see the very heart of the remnants of the supernova. So this is a way to see more completely the same thing with different types of radiation, and that's in fact what we do with our detector. You can even see, and so to speak, with neutrinos, which in our experiment I'll show you, we don't directly detect neutrinos. We can see the neutrinos in quotes by their absence without a balancing particle on the other side. This is an image of the Earth seen with neutrino detectors, and every one of those little spots is a neutrino source or nuclear power plant on the planet Earth. So here's a cartoon in our schematic of that photograph you saw of that young guy down there on the platform installing our detector. And it's made up of different types of what we call sub-detectors. And they play a similar role to the different telescopes that you saw taking pictures of that crown nebula. The particle beams go in this direction and in that direction and collide right in the very middle in this pixel tracker. I'll show you how that works in a minute. It's sensitive to forms of radiation that have a charge, like electrons and protons. Surrounded by that is two different calorimeters that measure the energies of particles that interact electromagnetically, like photons and electrons. And then the hadron calorimeter measures the energies of things like protons and neutrons. And it's made in a 4 Tesla, 3.8 Tesla solenoidal magnetic field to bend the paths of the charged particles so we can measure their momentum. And then there's these things called muon detectors on the outside of the experiment that were sensitive to the very penetrating form of radiation called muons. So each one of these sub-detectors then creates a very distinct pattern of information that we then use to reconstruct what's happening right here when the things collide. So this is an example of 5 different types of particles and how they typically interact with our experiment. So muons, this penetrating type of radiation, is the only type of particle that really makes it all the way up here. Hadron calorimeter measures the energies of protons and neutrons, and if they bend, that means they have a charge. If they don't bend, like this, it has no charge. It's not leaving any information in our silicon tracker, which is sensitive to things that have a charge, and deposit energy in little blips in our tracker. So use this information then to measure the charge, which way it's bending, how much it bends. So that tells you how fast it's going, what its charge to mass ratio is, its momentum, and then kind of what basic species of particle it is. Is it a muon? Is it something that interacts with the strong force, the electromagnetic force, and it doesn't have a charge? Here's a photograph of the detector that we built, our group, right here, which goes right around the beam pipe, right in the very heart of that gigantic thing. This is like, it's only about this big. And it operates on a principle that's very similar to the way that your camera works on your phone. It's not a charge-coupled device, but it uses the same type of idea of a pixel camera. So every one of these little units here is a pixel camera. And when a particle goes through it, charged particle goes through it, we reverse bias the silicon, as you guys are engineers, we reverse bias the silicon and pull out the charge carriers, the holes in electrons. Ionizing radiation goes through it, creates holes in electrons, which then drift to the anode and cathode of our little pixel, and we read out that charge. And with photolithography, you can lay out an extremely precise pattern of pixels. And so you know exactly which pixels it went through, and from that you can tell it's the location in three-dimensional space where the particle went, and you make that little picture of the curved track of the charged particles. And we do this at 40 megahertz, so 40 million times a second. These proton beams are colliding, boom, 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 making thousands of particles coming in this little nuclear explosion that is at an energy, average energy, that was present about a trillionth of a second after the Big Bang. So about a trillionth of a second after the inception of the universe, we're able to recreate the average types of events occurring in this very, very early stage of the universe. And the stuff that we're interested in studying, like this Higgs boson, are extremely rare in these collisions, even though this is extremely high energy and happening very frequently. And so that's why we have to collide these things at 40 megahertz to collect so much information, because it's about 1 in 10 trillion here of these events that have something that's interesting to us in quotes. And we can't control exactly what's happening because it obeys the laws of quantum mechanics, where we can't predict exactly which event is going to occur. We can only predict with what frequency it's going to occur. And the frequency with which these things occur, the probability is very low. So we have to collect lots of information, petabytes of data, hundreds of petabytes of data every year to be able to fish out the signals that we're interested in. After having done that, for the past 50 years, here's the periodic table that we've discovered. We've got these species of particles called quarks up on the top. The up and down quark make up the stuff that we're made of. Protons and neutrons are made up of up and down quarks. We've got the particles down here called leptons, like the electron and the neutrino that I mentioned. And those are these three things here, electrons, up and down quarks, make up all the periodic table of elements that we're made of, that stars create. And then surprisingly, somebody ordered 2 other copies of that menu item. And there are 2 other, and as far as we know, exactly 2 other types of particles, like the ones that we're made of. And they're unstable because there's not a muonic version of us somewhere. If there were, it would eventually decay into the electronic version of us. So this series of particles are unstable and eventually decay into the stuff that we're made of. But they're needed to make the universe work. If we didn't have those other species of particles, what we have wouldn't be working right. But we don't exactly know why there's exactly 3 of these copies of matter. In this column, you see the particles that carry the force. Photons carry the electromagnetic force that transmit the electromagnetic force between things with charge. The gluon and the Dominguez boson carry the nuclear forces. And then you've got this Higgs boson down here at the bottom, which I'll say a few words about. And then on the far right, you have the stuff that we know exists, but isn't explained by any of these other things in the periodic table. Dark matter must be some type of particle, I think, but it's not one of those. Dark energy, we really don't know what that is. And then gravity, we haven't been able to come to a quantum mechanical experimental understanding of how gravity works. Because, for the reasons that I mentioned, stronger than Earth. So there's something in the universe that is filling the whole place, doesn't disturb gravity or the electromagnetic force carriers, but it does disturb the weak nuclear force. And in fact, this Higgs boson is what is responsible for the origin of mass of these fundamental particles. So here's a little cartoon of what's going on. If there were no Higgs boson, everything would be traveling at the speed of light because it would have no mass. So all the particles which you see here as little shapes we would all be traveling at the speed of mass, the stuff we're made of. So really wouldn't work, right? We could not have the stuff we're made of traveling at the speed of mass. Instead, this Higgs field slows down particles like electrons and quarks, and allows them to acquire mass, so to speak, in proportion to how strongly they interact with the Higgs field. And in this collision of protons, we can create excite one of these Higgs bosons, which then decays into one of these particles that our detector's been designed to see. So the detectors and the cartoons I showed of how it works is what leads us to be able to recreate this type of image. Okay, this is all computer-generated information, but we put it into the form of a picture so you can kind of see. This is two very energetic photons, which are measured in our electromagnetic calorimeter. There's no charged track, so it didn't leave a track through our silicon tracking detector, so it was a photon. It interacted with our electromagnetic calorimeter. This is the energy is proportional to the size of this bar. And there's two of them that point back to the middle where this collision took place. And using just simple kinematics, you can take the vectors, the momentum vectors of those photons, and recreate the particle, the mass of the particle from whence it came. And that you do this over and over and over again, and you create a statistical picture of this Higgs boson in these various forms of interactions and decays. Here's a couple more pictures. Here's one where it produced two Z bosons. One of them decayed in one of the Z bosons. The Higgs decayed into two Z bosons. One of the Z bosons decayed into an electron and an anti-electron. So here you can see similar green bars in our electromagnetic calorimeter from the electron and anti-electron, but instead of the dotted dashed line, you see a straight line, or you see a solid line curving in opposite directions. So then that's how we know that instead of photons, this is an electron and anti-electron. And then the other Z boson decayed into a muon and anti-muon. And you can see that represented in the collection of data in our muon detectors outside. And here's another one. So, back to the beginning. So, what we've done here is 10,000 of us, approximately, have come together from all different countries, all different religions, all different backgrounds, together with our common God-given humanity, talents, and abilities to understand these questions that are bigger than us. And we did it together peacefully. Pharaoh didn't order us to go build it, right? We all freely chose to do this together. We all freely chose to do this together with the support of our countries, which allow us to do it. And we've done something that is profound. We've understood something about the actual creation and operation of the universe, which we would not have otherwise been able to do without each other working together in common cause. And I think that, for me, is probably our greatest accomplishment, is that we were able to do that. And if you look at this map, you'll see we've got Turks and Greeks working together, right? We've got Georgians and Russians working together. We even have Iranians and Americans working together. It ain't always easy, but we choose to do it. So that's what we do in particle physics. Now I want to tie it into a bigger picture of the STEM workforce and what a place like a Catholic college can do. I serve on the National Science Board, which is the governing board for the National Science Foundation. We're the governing body, so we approve the budgets, we hire the directors and things like that. We review it, and we provide advice to the President of the United States and Congress. And so we every 2 years, I think, produce a report with kind of the current state of affairs of interesting questions regarding science, engineering, and technology in the United States. And that's this report here. I'll show you a few pieces of information and slides from this report. It's not that long. I think it's about 40 pages. It's something that anybody can digest. You don't have to be a scientist to do it. It's written for the public as a guiding document, in fact. And the point we're trying to make in this report is that the United States of America really is a keystone in the world. in terms of science and technology and innovation. The United States is a special country at this particular time that ties together the whole world. And it's done in these categorize them in these 5 different ways. Our domestic STEM talent, so the students in this classroom, so to speak. International STEM talent, people that we collaborate with together in other countries, like my friends that were in these little red dots on the world map. New technologies that we invent and are working on here in the United States and with our friends around. The funding of basic research, so the kind of stuff that I do, which is basic research. And then collaborations. And all this together has allowed us to do this. This is a map of, a network map of papers published in 2020 on COVID-19 research. The size of each node or little dot represents the number of papers published by prime authors whose address was in that country. The connection or edges between the nodes represents a collaboration between between scientists in these 2 different countries on this particular paper. And the thickness of that connection tells you how many collaborations between those 2 different countries there were in papers published in 2020 on COVID-19 research. So you see here, the United States is in the middle in size and in connectivity. And this is what allowed us to produce COVID vaccines, was this type of international collaboration led by the United States. So the point here is that this is a key, right? And this didn't just happen in 2020. This is the result of what we've been doing for the past 50 years. It's also clear that we're not alone. It's not just the USA with nobody else, or the USA with just one other country. Oh, the other thing is that the closeness of the nodes represents how close they are in importance in this graph. So the closer they are, the more closely related they are in terms of the work that they're doing together. The further apart they are, the less closely they're related. So Argentina and the UAE are working together, but separately. The USA and China are tightly coupled here in this graph. So this is a plot over the past 20 years of in billions of dollars, of current year dollars, the gross domestic expenditures on research and development by a country over the course of the past 20 years. The United States is up here, and it's been growing. We've been investing or expending research dollars that allow us to do things like that COVID graph and the high energy experiments that we do, and it's been growing over time, so we've been investing and spending more as a country. The other countries down here have also been growing slowly over the course of the past 20 years. And what we've seen here is a dramatic growth in research expenditures by one new country player on the stage, China. Two more slides on some demographic data, because I want to start breaking down what we're doing in the United States. So here's, I won't go through all of it. Here you see the U.S. population broken down into a smaller number of demographic data on race and ethnicity. So the top bar there is the U.S. population of people who are getting degrees in science and engineering, so physics, biology, chemistry, mathematics, computer science, etc. In that age group of like you, right? Students like you and grad students. And you see in pink, Black Americans, in teal here, Hispanics, Asian Americans in purple, and then white Americans here in dark blue. And you see then the same, for the same group of Americans, people in the United States, people who are getting associate's degrees in these type of STEM fields. So you can get an associate degree in one of these related STEM fields, who are getting bachelor's degrees, who are getting master's degrees, and who are getting doctoral degrees, all normalized to 100%. And if it were the case that independent of this type of racial or ethnic background, these fractions were all the same, then that top graph would be repeated on each of these levels, right? So what you see here is a different distribution of these types of degrees amongst the different types of citizens in the United States. So that's of, in recent time, 2019. This is the situation today. Here's a graph of not what's happening in colleges, which is what's getting you these types of advanced degrees. This is what's happening before, as kids go through their elementary and high schools. This is a picture of a graph of a standardized mathematics test given to a fraction of kids in the United States at 8th grade to assess their mathematical aptitude for these different types of racial and demographic data in these different colors here that I showed on the previous plot, but also now divided into two separate parallel columns based on socioeconomic status measured by who's eligible for free and reduced lunch. So this is a proxy for income for the family. Okay, so if you're eligible, if you don't know how it works, if you're eligible for a free lunch, it means that your family makes less than a certain amount measured, given by the federal government, so that when you go to school, you have something to eat. And then those who are not eligible are above that particular threshold. So what you see in these two different parallel graphs is that there's a stratification based on the performance on this test based on your race and ethnicity, but also based on your socioeconomic status, and that those two, that the divisions, that these divisions between these different demographic data remain intact, but are correlated very strongly to socioeconomic status as well. Then the final two graphs are what people in the United States are doing in the STEM workforce in these various industries. So here we see it broken down in 6 different types of basic industries by sex, race, and ethnicity, and then nativity, like where you were born, and citizenship status. So sex, men and women. You see here computer, electronic, and optical product industries. In orange is men, and blue is women. Machinery and equipment, scientific research and development, the pharmaceutical industry, electrical equipments, and software publishing. Same here, set of industries by those who are in one of those underrepresented different classes, different statuses in these same different categories. So you can see most of them are just by definition, in a sense, not underrepresented. And then by nativity and citizenship status. And this is an interesting graph, I think, because you can see the large role that our nationalized citizens are playing in the United States. And those are the people here represented by this purple bar, and then the lighter shade of purple are recent immigrants to the United States working here, doing this work, who are not yet nationalized or won't be nationalized citizens. So foreign nationals working in the United States. And so this is playing a very large role. These people are playing a very large role in the operation of the United States of America, both native-born, naturalized, and foreign. When you boil that all down to what it means, what do we need to do to more fully capture the talent that we have here present in the United States of America, to fully capture that human capital, we would need to double the number of women in this STEM workforce. So we're missing about half of the possible number of women that could be participating, if they so choose, in the STEM workforce. We need to triple the number of Hispanic and Latino STEM workers. We need to more than double the number of Black African American workers in the STEM workforce in the United States. So those are the people, us, who are present in the United States, who are missing from the STEM workforce, who we need in order to achieve and maintain this keystone status as a country. So it means to maintain this position as the keystone status, not just for ourselves, but for the world, as the United States being this keystone. It means strengthening these international collaborations and engagements, not withdrawing from them. It means being a dependable partner, international partner, fostering open exchanges of ideas and people with like-minded countries who share our values and freedoms. It means being an example that people want to come to. It means being a place where all the talent, God-given talent that we have present, has the possibility to participate in these activities. And I challenge you that a place like Santa Clara University is such a place. You are placed in Silicon Valley in California, surrounded by these kinds of people that you saw on these graphs that are missing. You are a Catholic Jesuit institution that was founded at a time in the United States when Catholics were persecuted because they were Catholic and excluded explicitly from being able to participate in the culture of the United States. There was a time when you couldn't go to the Protestant colleges, get an education because you were a Catholic. And the Catholics formed their own schools so that they could educate children. They formed their own colleges so they could educate adults. And they could have just done it just for Catholics. Logically, they could have just made the Catholic schools just for Catholics because they were trying to take care of Catholic kids and Catholic adults and give them education. But instead, they opened the doors for everybody. They opened up these Catholic schools for everybody to come to. That's why Santa Clara University is needed by the world. Because this is what we do. This is what we should be doing as Catholic institutions. Not just because it's good for the STEM workforce, but because it's what it is that God is asking us to do, because we are all children of God, made in His image and likeness. And by participating in that plan, we make things better for the world. That's what we should be doing. That's why I'm super glad to be here to visit you guys. Thank you very much.
Thank you very much for a very insightful and thoughtful presentation. I think there are lots of questions.
Questions. I have two questions. One on the physics thing. What is a black hole?
What is a black hole?
The second question on the STEM. You showed that we should double this. Let me take this out. No. One is question on the black holes.
Yeah.
Okay. The second question on the STEM. Your point is well taken, the way the graph shows this. What is the nature of efforts we should make to double that, triple that, or that thing? What the nature of, can you talk something about what are those steps we need to take?
Okay, yeah. So the first,
I think spoke loud enough, isn't it? I don't care. Another question could be, if the gravity is there, this is very typical. Why the universe expanding then?
Yeah, exactly. That is the question. In fact, the question is why is the universe accelerating if gravity is there?
Anyway, this is it. I'm sorry.
Yeah. So the black hole question is due to the fact that there's a constant value for the speed of light, and once gravity becomes strong enough to prevent light from being able to travel at the speed of light, this black hole forms. It's still something we don't really understand because we don't truly understand gravity, but we do know that they exist, and they're important for the operation of things like our galaxy. That's what lies at the heart of our galaxy. Question about the STEM workforce: what can we do, to change this picture? Is a good one, and I think you shouldn't give in to despair, because this is a huge problem that's bigger than all of us. It's bigger than
this university, it includes the whole entire history of the United States in our current situation, and instead we should focus on what can we do as individual people working at this university. Because you have a job. You're a university, your job is to produce research, to create this Catholic Jesuit education for undergraduates and graduates, and to play a role in your local area here in Silicon Valley in the United States. And we should ask ourselves, what can we do as an institution that is achievable? We won't be able to solve all of it, but we can pick off some of these things that we're able to do and do them, try to do them. I think that's the approach that I would suggest that we undertake. We can make statements about what's wrong with this picture. Can't change it all, but we should give ourselves over to trying to pick off the parts that we can do that are good for us too, that help change that picture. Yeah, Enrique.
Thank you.
Yeah, switching on. This is switch.
Thank you, Aaron, for your wonderful lecture. Even associate scientists understood a little bit of what you said to it. So that was great. Great achievement. I have two questions. The first one, in the social sciences, we're very interested in collaboration.
Yeah.
What motivates individuals, especially in a diverse community, to collaborate with each other? So my first question is, will you tell us a little bit about what do you think is motivating this community of scientists to collaborate with one another? That's my first question. The second question, I have been actually very concerned about your second part of the lecture about the question of diversity. And recently I published a study looking at what I call transition rates. And the transition rate is the number of students who actually move from one grade level to the other. In other words, how many high schoolers actually go to college, how many people from college go to graduate school. If you look at the demographics, there is an inverse triangle. About 85% of Hispanics graduate from high school, but only about 26 go to college. Why do you think that's the case? What can we do to reverse that relationship?
Yeah. So I'll start with that last one here, because there's some interesting data packed into this graph here. What I don't have is the graphs that speak exactly to your question, Enrique. But things have actually been getting better in the United States over the course of the past 50 years. For example, the high school I went to in Albuquerque, New Mexico, which is predominantly Hispanic, less than 50% graduated from high school. And now it's 85%. Okay, so that's an improvement, I would have to say, right? I left behind half of my friends. Now my kids would only leave behind 15%. So things have been improving. And if we look at now where they go, if they choose to go or able to go to college, what are they doing? You can see that the ratio here of this blue bar, which represents Hispanics getting associate degrees, as opposed to bachelor's, master's, or doctoral degrees, is actually overrepresented. So in fact, Hispanics are going to get associate's degrees, which more easily, more quickly lead to a higher paying job without having to go to 4 years of college and go into debt. And those are primarily community colleges. So it's a step. It's the next step that we see being taken. And I take this not as a negative thing. I see this as a positive step. If it remained like this for 50 years, then I would be wondering what's going on. Why aren't Hispanics going to get bachelor's degrees? But I think what we see is that they're stepping into, they're fighting their way into this next tier, at least in the STEM fields. This is just specifically degrees that are classified here as science and engineering.
What about the first question?
What was your first question, Mike?
The question about what inspired this collaboration among such a diverse community of scholars?
So, for me, what inspired the collaboration was necessity. We needed each other to answer and to do these things that one man couldn't do, right? This discovery of the Higgs boson could not have been done by one human being. And that one human being would have to live for 1 million years and have the capability to do all of these things. And the only way we could do it was by working with our brothers and sisters who were smarter than us, who have other types of talents, and to do it together at the same time over the course of something that can fit within one human lifetime, right? Those are like the constraining parameters that allow us to do something that we thought was important and achievable. So in that one example of particle physics, that's why we did it. And it also, once you do it, started this as a student, right? I've been a particle physics as a physicist my whole career. It's always been collaborative. I went and learned foreign languages that I would never have learned. I never thought I'd have to learn French. I wish I had taken it in school because I had to learn it the hard way in France. But now I speak French, and so it's changed my life to be able to go and work with these other kinds of people, and it does that for all of us. And when we come back from that, we bring that with us. We want to continue that. I want to pass that on to my students. So now I make my poor Hispanic students learn French, so they can go work in Switzerland.
Other questions? Yeah.
Two quick questions. So you showed the periodic table for.
Yeah.
So there's a top quark and bottom quark.
Yes.
I've also read that the physicists sometimes they're calling it as truth and beauty.
Yes.
Are they just being physicists, or there's a philosophical significance to that?
Right. So his question is, why do we call these things these stupid names? That's and the answer is because physicists don't have a life. Yeah, we had to give them some kind of names, and physicists don't get out enough, and so we come up with these names. Up and down is because they fit into this doublet, and we place one on top based on its quantum mechanical properties in this doublet, and then we find out that there's these two other copies, and we could have called them, up 1, up 2, up 3, or something like that. But instead, we thought it would be kind of cute. So top and bottom also had at the time other sort of names that had started with the letter T, like truth and beauty.
So
We thought it was poetic,
interesting.
but no other reason.
And last quick question was, so the particles, they don't experience time, correct? If I'm not wrong.
Particles don't experience time?
Is that
No, they do.
They do?
Yeah. In fact, these particles all have a lifetime that's greater than 0, or infinite in the case of photons or electrons. But they do experience time for sure.
And the second law of thermodynamics, that's the only law that has time in it. Does that fit in with this particle? That's completely like Latin and Hebrew at this point.
Not quite sure about how to answer that second question.
I see.
But yeah, for sure. So the second law of thermodynamics does play a role in the evolution of the universe, and the initial conditions of the universe, and that's a great mystery as to how the initial state of the universe is what it was in order for it to work today. It doesn't make sense if you just kind of take thermodynamics as we understand it now and sort of if it were truly random that the universe came into existence, it seems to be impossible for it to have actually happened the way it did unless it were set up precisely to work the way it does. And that leads to a whole other set of theological questions about how the whole universe is put together in this exquisite way for us to work.
Actually, I have a two-part question related to what you said. You're a very strong Catholic, and I wanted to know how you merge your faith with what you study as far as the origin of life. Do you believe in creation or what do you call it? Evolution, or the third one is intelligent design?
Yeah.
And how does this play a part?
Yeah, so I've been a Catholic my whole life since a little boy. Of course, I have learned more and more about my own faith as a Catholic as I get older. I've also been, interested in science even since I was a little boy, and was not a physicist as a little boy, but became a physicist as a man, and have learned more and more about physics and how the world works. And both of those two things have been me, growing up and becoming a man. And both of those halves of me have been in harmony with each other the whole time and have been strengthening each other. So me, at least for me personally as an individual, Aaron Dominguez, those two things, being a faithful Catholic, a man of faith, a believer, and being a scientist, have not been in conflict with each other, and in fact have mutually strengthened each other. And these theological questions seem to be compatible with the scientific questions as far as I've been able to discover. And it follows, as a Catholic, it follows the logical underpinning of our faith, which is that truth cannot negate truth. If two things are true, they're both still true. So God is true, and the origin, the creation of the universe that came out of nothing is true. Both of those things are still true. And as believers, we have a hierarchy of where the truth comes from, and that's God as the capital T. But so those two things can't like fight each other. Both of those things have to both be true. And the more you learn about this periodic table and the way the universe works, of course, I mentioned that we don't understand how 95% of it works yet, so there's still a bit to be understood. But the fundamental constants that are present in this periodic table and in others, like the mass of the electron, the strength of the electromagnetic force, the nuclear energy levels present that exist to create carbon from the kind of nuclear reactions that happen in stars. There's about 20 of them. They all could be different values within some sort of reasonable range for a universe to be. But they all have to be exquisitely exactly what they are for the universe that we exist to be. But there's no physical law that tells us that they should be so. And especially this one about the initial entropy of the universe, that one, when you calculate it, it's effectively mathematically impossible for it to have started with such a low entropy for the universe to exist. It's effectively mathematically impossible, unless there's something we profoundly misunderstand about everything. And so, what does that mean? I mean, it means the universe didn't randomly come into its existence from just entropy, an entropy calculation. It means that it was set up that way. And this multiverse thing is something that people have come up with. Well, okay, maybe we're one of an infinitude of universes and we just happen to be the lucky guys. But that doesn't sit so well with me as a great explanation for how the world really works. And it begs the question of, well, who made the multiverse? So for me, those things they all stack up and reinforce each other for me as a scientist and a Catholic.
Thank you. I have a second part to the question. How many people have watched the movie The Most Unknowns? Anybody? Okay. It's a documentary, but I recommend it. But that movie had a lot of things that are unknown, including this, what you just mentioned. But my question is this. Knowing that physics is at fundamental level compared to, like, say, chemistry or even biology, how will these new developments impact eventually the study of chemistry and also biology?
They're certainly related, scientific realms, but they're not completely within each other. I mean, quantum mechanics has a limit to being able to explain biological systems. It doesn't play a huge role in the way that our bodies work at the macro level. So there are certainly realms of understanding that are important, because if it didn't exist, then the rest of it wouldn't work. But they don't have such a direct. Quantum mechanics doesn't have such a direct impact with this room and our human experience. So, there certainly are limits to how much this thing can tell us about the more complex emergent phenomena like biology.
The reason I ask is because, for example, atoms come together to form molecules, right? But if you know that an atom is even much bigger than what it was, a lot of things, then it will eventually change the way chemistry is taught, and also change the way biology is taught. So that's what I was trying to allude to. Which,
yeah, I mean, it is true that, especially in chemistry, not so much in biology. Although, I mean, if you think about the photoelectric effect, which is kind of at the heart of things. That's a quantum mechanical effect, and that does have a biological impact, because we have photosynthesis, converting photons into capturing and converting photons into other forms of energy by plants. So there are some very specific examples of how these different realms connect. Magnetism is another one. Having a magnet is effectively a quantum mechanical effect.
Question? Oh, go ahead.
Thanks for your talk.
Can you turn on the mic?
You have to turn it on. Sorry.
Thanks for the talk. It was very informational. I have a question about the nature of the experiments in the Hadron Collider. So, from what I understand, there's protons that accelerate throughout the collider, and they come in from opposite directions.
Right.
And they collide.
Yes.
So the experiment itself starts off with protons. How is that telling us about the origin of the universe, where the hypothesis is it starts from nothing?
Yeah. Well, this experiment is not really creating, universes over and over. Okay, the Big Bang comes from cosmological observations. This thing of kind of like pointing the direction of everything back to this initial, very small version of the universe. That's not something we would discover in these particle collisions. So that's a separate observation. Okay. And what we've learned from that is that because the Big Bang is a scientific fact that it came out of nothing, when it was an extremely small version of itself in its very most earliest stages, because everything was packed in there, it was super, super hot. And it was so hot that we're able to actually, with these particle beams, recreate that temperature in a sense of particles that are interacting when they were present in this very early Big Bang version of the universe after the Big Bang. So our accelerator experiments don't tell us that the Big Bang happened. It just allows us to study the stuff that happened right after it.
Mm-hmm.
Yeah.
And another question about the gravitational force. Like you mentioned, you're able to move things against the gravitational force.
Yeah.
But you have a limit. You can't pick up an airplane.
True,
right?
I can't pick up an airplane.
But gravities can make the airplane fall down.
Right. Yeah, and of course I can't defeat the entire planet Earth on everything, or I'd be Superman, right?
Yeah.
So, but I'm at least super enough to defeat it for this. But I can't defeat it. I can't defeat the nuclear forces.
Okay.
And turn with my finger this into a nuclear bomb by squishing the
harm
atoms,
it
right?
at a nuclear
Yeah.
level.
So I can't, and I also
those
can't.
forces are stronger.
Yeah, and also the electromagnetic force is stronger because what's preventing me from putting my finger through here is the electromagnetic force.
So okay, I understand now.
Yeah.
You're saying that the
It's like a
things that are
hierarchy.
holding it together
are
more
stronger than
powerful.
me
Yes.
as a person, but
Yes.
I happen to be stronger than the whole Earth, which is a pretty big thing.
No, I understand now.
Yeah.
I understand now.
Yeah.
Other questions, please?
Well, okay.
No other questions? Let's give him a
Thank you all very much.
I have a few closing remarks, please. Let me
Okay.
just thank the I want to thank the acting president, Lisa Kloppenbach, for her support of this event, and also the acting provost, Ed Ryan and Kate Morris. Thank you, Dean Elaine Scott, for your support of this program, and the department chair of physics department. Thank you for coming. Thank you for helping to spread the word. Also, Shubha Krishna, department chair of electrical and computer engineering. She's gone. And all the faculty staff, thank you for coming. I want to tell you that we are looking for speakers for the next quarter. So if you have any suggestions, please email me. And one more time, let's give a round of applause to us.
Thank you.
See you next quarter.